The force of gravity equals what we call an object's weight, and gravity always points down, which means that the y component of gravity in a standard coordinate system should be equal to minus mg, provided mg represents the weight. So this is kind of establishing some rules here for working with the force of gravity. We've already been kind of using them, but I'm stating them more formally now. One of the issues that comes up, though, in this topic on gravity, mass, and weight is the distinguishment between weight and mass. As we just said, weight, which is really a measure of the pull of gravity, is equal to mg, is equal to F sub g. Mass, on the other hand, is equal to the amount of matter and is what we represent with the symbol m. In that sense, since weight is how strong gravity pulls on an object, mass, on the other hand, could be thought of as the measure of an object's inertia. In that sense, the more massive an object is, the more inertia it can be thought of as having. And it's maybe a little weird to say it that way. This is kind of a conceptual definition that maybe not every book out there states it exactly this way, but it's kind of a way of conceptually associating mass with what it is really associated with. It really is a measure of an object's inertia in the sense of how much it resists acceleration following Newton's second law. Weight, on the other hand, being related simply to the pull of gravity, that's not necessarily something that is a measure of the object itself, because it really depends on where it is. An object might have a certain weight here on Earth, but you take it to another planet or to the moon or something like that, or even far away from any object, and weight will disappear just as gravity disappears, but the object will continue to have an amount of inertia and the property of inertia and an ability to resist acceleration that corresponds to the amount of mass that it has.